Annenberg Media.
Researchers conducted a series of interviews with middle school students after they had completed a course in physical science. About 2/3 of the students said that air is made up of tiny, invisible particles. The rest indicated that air is one smooth, continuous substance. Then the researchers provided the students with a hand pump and a closed flask. They asked them to pump out some of the air. After pumping, the students came up with a wide variety of descriptions of how the air would look if they could see it. For those students who described air as being made up of separate particles, we're left with a question of widespread disagreement. What's in between the particles? Welcome back to Essential Science for Teachers. I'm Robin Moriarty, an elementary school teacher from Needham, Massachusetts.
And I'm Sally Balunas, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. You might think that there's an easy answer to the question of what's in between the particles of a gas.
Matter, whether the air we breathe or this glass of water or this table, all seems to be smooth and continuous. What could possibly be in between the very fabric of this matter? We'll explore this question and many others in this session.
In our last session, we picked a working definition of matter, that is, something that takes up space and has weight. We compared the properties of solids, liquids, and gases and developed a classification scheme based on their similarities and differences. But we haven't really investigated why solids, liquids, and gases are that different.
In today's session, we will explore a single explanation or model of matter to help us to understand the very different characteristics of solids, liquids, and gases.
By model, we don't necessarily mean something that you build out of wood and glue. In the scientific sense, a model is a testable idea or theory. It's something created by the human mind that tells a story about what happens in nature.
We'll explore how the very different characteristics of solids, liquids, and gases can be united in one useful explanation of matter. The model that we'll present traces back to the Greeks, but it attained its modern form in the early 18th century. It's called the particle model of matter, and is based on the idea that all matter is composed of tiny particles. We'll find it to be a useful tool for predicting the behavior of matter under diverse conditions.
As an astronomer, I use models all the time. In my work, a model is only as good as the predictions it makes. We then go out and test these predictions with new observations and new data. If the data fit our predictions, we keep the model. If not, we must either revise the model or throw it out and come up with a different model.
The particle model has stood up to scientific examination and has been useful in predicting the properties of matter. While many of my fourth grade students can use terms that relate to the particle model, like atoms and molecules, they don't always have a clear idea of the particle model itself. Although the particle model doesn't usually appear in the curriculum until later grades, it's important for elementary teachers to set the stage for this idea through the curricula that we do use, when, for example, teaching about the water cycle. And certainly many students will bring some knowledge of atoms, molecules, and particles to the classroom, along with other questions that we might need to address.
In an interview, Siddharth, a third grader, is presented with a question. What happens if you tear a piece of foil and divide the resulting pieces again and again? As you listen to his ideas, do they fit a particle model of matter?
Was that pretty easy?
Yeah.
Okay.
But tearing it from like there is really hard.
So if you were going to go on tearing, let's just go with one piece. And if you were going to go on tearing, would you be able to keep on tearing it?
Wait. Wait, so I'll tear this. Well, if my fingers were small enough, I'd be able to, but like the size they are right now, would not be able to do that.
Yeah, we actually have a few things here that might help with that. We have some scissors and some tweezers to hold it with, if that'd be easier.
That's probably like the smallest piece I can get.
Okay. Could you draw that same thing but really magnified? Like what it would look like if it was magnified a lot by a real powerful microscope?
Something like that.
So it would have the jagged edges. And would it still be shiny?
Yes.
Okay. Would it still be bendable?
Well, it depends if you had something like really small tweezers like this in order to pick it up and then bend it.
Okay. If you could keep shrinking yourself down and seeing a smaller and smaller piece, and were cutting it, could you just keep cutting it forever?
If you shrunk that small, yeah.
Would there ever be a point at which you couldn't cut anymore?
I'm not sure, because it might like go away. It might like disappear or be gone, or it would be really, 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 really small. I think it would just be really, really, really small.
Okay. Would it still be aluminum foil?
Yeah.
Okay.
Although it would be shrunk aluminum foil, but it still would be aluminum foil.
Siddharth is convinced that however small his pieces of matter are, he'll still be able to divide them further. In other interviews, Siddharth has described and drawn molecules and atoms, but he doesn't seem to connect them with the aluminum.
Siddharth's view of matter in this interview is closer to the continuous model of matter that goes back at least as far as the ancient Greek philosophers, and particularly to Aristotle.
Aristotle didn't spend very much time experimenting. Beginning with a few observations of a general nature, he used logic and reason to construct all-encompassing models, building only on prior principles.
What was the observation that Aristotle used as the basis of his theory of matter? Science historian Dr. Al Martinez.
The continuous model of matter is a way of summarizing many different perspectives that throughout history were advanced, essentially summing up to the idea that matter is not characterized by the kind of structure that we would assimilate with something like a honeycomb or a net or a grid of any sort. It doesn't have gaps within it. It's more like a stone, like a piece of glass. It's smooth, it's even, it's homogeneous, so that the parts that make up the matter are immediately connected and adjacent to one another.
Aristotle didn't observe any gaps or voids in matter. Take, for example, this piece of glass. We can't observe any texture or gaps in it. On the other hand, take this sponge. It contains many gaps. If we immerse the sponge in water and squeeze, we can see bubbles released from these gaps. Aristotle explained this by saying that in his model, air infiltrates and invades all substances and fills any gaps or spaces.
Aristotle's idea of a continuous model of matter lends itself to our everyday experience. To Aristotle and to other thinkers, for more than 1,000 years, it seemed to be a logical and complete model of how the world is constructed.
Part of the appeal of the continuum model of matter is that it harmonizes very reasonably with what we observe. By contrast, if you imagine that matter is not continuous and that there are somehow spaces or interstices between little bits of matter, that's something that you don't actually experience. You don't experience any holes or gaps in a piece of glass or in a table or in a stone. You don't experience gaps in the air that we breathe. You can imagine that there might be such gaps, but that's not given to experience. So actually, it is a major conceptual leap forward to conceive of the alternative to the continuum hypothesis, to conceive that is that there is empty space and little hard, solid, impenetrable particles floating about in it. That's not what we experience immediately.
Imagine, if matter is composed of little particles, what might they look like? What would happen if we could somehow invent a new kind of microscope, one that would let us observe these particles directly? What would they look like?
We asked a 5th grader, Clara, who already knows something about atoms, to answer this question. As you watch, you might reflect upon how your mental picture of a particle model of matter differs from Clara's.
What do you think this aluminum foil is made out of then?
Well, definitely aluminum and atoms and stuff like that.
Mm-hmm. Aluminum and atoms, are they the same or are they different things?
They're different because, well, atoms are what make up everything, and aluminum is an element that you can't find in every single thing.
Mm-hmm. This aluminum foil is like almost completely pure aluminum. And what I wanted to do was for you to draw what you think it looks like under that little dot where we had there, blown up this big, what it might actually look like in the microscope. Okay, can you tell me about these little dots versus the bigger dots?
These would be when you got all of these together, then it would make up one of these. And so this would be the aluminum, this would be all the atoms, and then you put them together and it would make the aluminum.
So these little dots, these atoms, if you magnified up these pieces, these bigger dots, you'd see them all full of the little dots.
Yeah.
Oh, okay. Would these big dots be sort of like mirrors, do you think?
Yeah. I think these are sort of like this, except even smaller.
Do you think these big dots would be like foldable?
I think so. But it might be more solid, like a soda can.
Harder to fold.
Yeah, but in aluminum foil it might not be, but in a soda can, if you did the same thing, it might.
Well, would the dots be like flat or would they be like round? What do you think?
I think they'd be the way that this is. So if it was flat, then they would be flat, and if it wasn't, then they wouldn't be.
Clara says that if the object were flat, then the particles that make it up would be flat. In other words, that the properties of the particles are the same as the bulk properties of the matter we observe with our eyes.
Let's think about that. In our model, the particles of a pure substance are all pretty much the same. We believe this because scientists have made many observations of different samples of pure substances and found that each has identical properties. Clara's particles are inconsistent with her idea of atoms, which is why I think that she believes that there are two kinds of matter in the aluminum. The bigger dots have the familiar properties of aluminum, and the smaller dots are atoms, which maybe don't have any properties. They're just atoms.
Do you think that the little dots have the same properties as aluminum?
No.
Do you think they're shiny?
No.
Do you think you could tear them in half?
No.
Do you think you could bend them? No?
Mm-mm.
Do you think
Well, you might be able to, actually, because if you can bend the aluminum foil, then if it's in the aluminum foil, then you could bend it.
But would the dots be like if you could isolate one of them?
Yeah.
Could you bend one of those what you called atoms? Do you think you could tear it in half?
I think so, because They're smaller things than atoms,
So,
like electrons and protons and stuff like that.
well, what do you think you could do with the little dots then? Why don't you tell me a little bit more about them?
Well, if they were atoms, then they'd have a nucleus, neutrons, protons, electrons, and all that, the things that make up atoms. So then, since they had smaller things, you could make that in half. But then I don't know if you could really cut like protons and electrons because you can't see those in a microscope. I don't think.
Do you think you could cut the dots, like the big dots, in half if you had something really sharp?
Robin, is this a commonly held perception on the way toward a more concrete understanding of the particle nature of matter?
I think so. From the student's point of view, it's hard to see how the properties of aluminum that we observe, like shininess or the ability to bend, can be produced by tiny invisible particles. But if we as teachers can be aware of how bulk properties of matter arise from the aggregate properties of tiny bits of matter, perhaps we can help communicate this to our students.
What does it mean to say that something is solid? We all agree that metal objects seem solid, that this heavy brass, in all outward appearances, looks completely solid and uniform in composition. But doesn't the sand on a beach, seen from a distance, seem just as smooth and uniform? Until one examines closely the grains of sand, it's hard to imagine that this smooth, continuous surface is actually composed of millions of tiny grains. Each tiny grain may seem insignificantly small and light, but taken together, they would have a great deal of weight and take up a great deal of space.
The question that confuses students today is the same as the one that the Greek and Roman philosophers wondered about. How can a model of matter at scales that almost defy the imagination explain the properties that we observe and measure at human scales?
Let's perform a classic thought experiment used by the physicist Richard Feynman and many others and take a trip into a drop of water. With the naked eye, water looks smooth and continuous. If we place a drop under a microscope and magnify it 200 times, our drop of water would appear as if it were a meter in diameter. We can begin to make out bits and pieces of material floating around. Occasionally, perhaps even something alive, like this paramecium. Let's magnify our drop of water another 200 times. The water drop would appear twice the size of a football field. We can begin to see some motion. This motion is the particles of water themselves, but still too small at this magnification to make out the individuals. If we magnify this scene 500 times, we can examine the individual particles or molecules of water. At this magnification, the drop of water would appear to be 100 kilometers in diameter. We represent the water molecule as having 3 parts. The large sphere in the center represents an oxygen atom. The 2 smaller spheres, hydrogen atoms. We know all this by indirect measurements. We'll treat the water molecule as what it is, the smallest possible unit or particle of water. However, we should realize that this can be further broken down into even smaller parts. But if we were to do this, then we would no longer have water.
It's hard to comprehend just how tiny the particles of matter are compared to objects in daily life. To give another example, also borrowed from Feynman, if I wanted to enlarge a hydrogen atom the smallest building block of this apple to the size of the apple, I'd have to enlarge the apple to the size of the Earth.
It's not surprising that any given group of students will most likely have a variety of different ideas about the nature of matter at extremely small scales.
Let's return to our interview with Clara to ask, what's in between the particles of aluminum?
I had a question about the spaces between the big.
There wouldn't be spaces because that would mean that there would be like holes between the aluminum. But if you draw it, then it would just be all purple. It wouldn't be any space, because if there was space, then you couldn't really have the aluminum.
Clara has represented the aluminum matter as discrete dots, but she doesn't recognize the inconsistency of this idea with her idea that a real drawing would be all purple with no spaces. If they are separate bits, they exist in a background of something else. But what, if anything, is that something?
And how about the atoms then?
I think atoms are circular.
Okay. Well, did you ever have a big pile of marbles that are circular?
Yeah.
But there's spaces between them. They're like holes.
Yeah.
What do you think is in those holes between your atoms?
I think there's space, there's space between the scissors and the aluminum, and there's space between a lot of stuff. But it still is something, it's not absolutely nothing. Like the table is still there, and they're both on the table.
So between those atoms,
There is
you said there's
something.
space between them.
Yeah, it's because
but
it's
there's something.
one
But what is
thing.
that something, do you think?
Air, or maybe just like the nucleus or something like that.
Okay, and why are they things? Couldn't it just be just solid aluminum all the way down?
I don't think so.
Clara's mental image of matter is that there are particles or atoms in the aluminum, but that there's still something in between those particles.
Science education researchers have documented similar ideas in many children of this age group around the world. Even though they may mention atoms, after all, the word is in common use, their concept of empty space is not fully developed.
It's not just children. Many adults have difficulty thinking of empty space. In ancient times, the existence of empty space, called a void or a vacuum, was rejected by many thinkers. After all, where do we experience empty space in daily life?
To find an answer, we'll visit the MIT Plasma Science and Fusion Center, where Bob Childs is the vacuum laboratory supervisor.
I'm Robert Childs, and I work here at the Massachusetts Institute of Technology, the Plasma Science and Fusion Center, and I'm a vacuum engineer and a lab supervisor. And one of the roles that's very, very much necessary is a vacuum engineer, somebody who studies the necessary pumping devices and puts them together in the right order to achieve the high vacuum that is necessary for fusion.
The concept of a vacuum was demonstrated by the Italian physicist Evangelista Torricelli in 1644. Torricelli sealed a glass tube at one end and filled it with mercury. Then he inverted the tube into a bowl, allowing the mercury to run out. The space that appeared in the top of the tube is a vacuum, empty except for a few wisps of mercury vapor. Living at the bottom of a sea of air, we are not usually aware of the weight of the air pressing down around us. But demonstrations such as Van Gurick's showed that if two hemispheres were pressed together by pumping the air out between them, even teams of determined horses couldn't pull them apart.
My hero, Otto von Guericke, used using his hemisphere and vacuum, he was able to prove that we're under tremendous pressure all of the time. That's right, the atmosphere is pushing on us right now. We've got over 15 pounds per square inch pushing down on us all the time. The pressure all around us, pushing on the hemisphere, holds it together. There's no glue, it's just the pressure of the air pushing on the hemispheres to hold them together. Step back. Now you can hear the air going back and up. Wonderful.
It's important to understand that what vacuum is all about pressure. Right now, when you're sitting in the room, you have 15 pounds per square inch, approximately, of pressure exerted on your body. We're actually just changing the pressure. We're making it less than atmospheric. As we start to take the gas out of the chamber, the atmosphere away from the chamber, we're actually just changing the pressure. We're making it less than atmospheric. And that's what vacuum is all about. As you get lower in pressure, the pump's efficiency drops off. So in that case, if you're trying to go to a lower pressure, use a different style of pump called a turbomolecular pump. Particles that are randomly bouncing around inside the vacuum chamber. And what they see is a blade of metal, and that blade is moving faster than they are. So as the particle comes in contact with the blade, it is literally bounced down, lower down into the chamber. And it meets another rotating blade, and so on and so forth. It gets to an area at the bottom of the pump where the compression is a 1500 to 1, and at that point it can be pumped away with a standard mechanical pump. You now have reached a point where the particles are bouncing around, and there's collisions taking place every now and then, but very randomly with each other. And one has to think of what's going on between the particles. Well, in fact, there's nothing there. It is empty space. It's just open space with nothing else there, just waiting for a particle to pass through it.
Bob has shown us a practical demonstration of the particle model. If we're going to accept this over the continuous model of matter proposed by Siddharth and Aristotle, we have to make sure it fits all of our observations.
Here is where experiments are essential. As scientists gathered evidence that can be explained better by one model than by the other, they began to have a reason to choose one over the other. But which experiments? We asked students to compress a gas, air in a closed plastic syringe, and describe what's happening at a microscopic level.
This simple experiment can be quite thought-provoking. We have matter not only changing its shape, but changing its volume, the amount of space it takes up. Joanna demonstrated the compressibility of gases by squeezing air in a syringe. By pressing hard, she was able to force the air to take up much less room. When she let go, the syringe bounced back to its original position. How might this be explained in terms of a particle model of matter?
Now, we got all the air in. There are like little atoms all around. Now here the air starts to go out. You know my idea now? Maybe like the more it pushes, the more are trying to escape, and it's harder. So then less comes up to 20.
Hold on, where are the atoms?
These are the atoms, like 1, 2.
But look, aren't the atoms down here? Because here's your plug.
This is the 20 line. So that's
so
when
we've pressed
we
it
had to
right.
stop. Now right here it probably has a lot of atoms, and well, not that much, but a few, and then it's hard to push through those atoms.
Okay.
Pretty hard.
So what happens to the atoms when you press down here? You sort of squish
there will
them?
There will always be 1 or 2 in them. Then imagine this had like a lot. It would like escape.
Yeah.
And go around to the normal air, but there would always be like 1 or 2 fourth 5 atoms inside this.
Okay.
Because in the air, the atoms are farther apart, but they're still there.
Okay.
Joanna drew the particles of air closer together when she pushed the piston of the sealed syringe and compressed the gas. When she released the syringe, she drew the particles farther apart. But it's hard to know what she meant by atoms. For example, she seemed to think that there were only a few inside the syringe. We asked another student, Tanzila, the same question. Does Tanzila support or refute your idea of what gases look like at the microscopic scale?
But if we use, like, if we focus this powerful microscope on what's going on inside here, what do you think would come up on the monitor?
Maybe tiny, tiny objects that, because we don't know what we're inhaling in the air. Maybe there's different things, or pollen, or something from the flowers, or things like that, or stuff out of our clothes like that.
Could you draw, when it's compressed down to the end, what the syringe looks like? And instead of it all being full, it's just the plunger is down to about there.
So I think there's a big force, and this is closed, right?
Mm-hmm.
Okay.
Closed.
So the air is trapped in here. So I think the air's trying as best as it can, because when we're forcing the air to try get out, it can't get out. So it's kind of like that.
Tanzila didn't draw the individual particles as Joanna did. She seemed more interested in the push that the air was exerting when she pressed on the plunger.
She gives air human-like qualities. The air is trying to get out, to explain the force she feels. Neither student really addressed the question of what causes the force that they feel pushing back on the plunger. And there's even a more fundamental question. If I weigh the syringe before compressing the air inside, will it weigh the same as after? It weighs the same. And if I release the piston, it travels back to its original position and still weighs the same. This presented a dilemma for proponents of the continuous model.
How can it weigh just as much if it only occupies half of the volume? If allegedly some of the particles zipped right out, you emptied some of that container of matter half as much, and it weighs the same thing. It's a serious puzzle. It's a serious problem. Consider the opposite relation. Now, having taken it from this size, now you expand it by lifting the plunger. What the plenum theorist would say is, look, there is no empty space. Matter has flooded in through the tiny interstices in the walls of the container. It has flooded in. And again, you ask them, if it has flooded in, so now there's twice as much, how come when you weigh this container, it weighs just as much as when it was half the size?
The particle model is a much simpler explanation than any that was offered by scientists who believed in the continuous model. Let's just summarize what our model is so far. Gases consist of tiny particles. These tiny particles are surrounded by empty space. When gases are compressed, the particles are squeezed closer together. When gases are expanded, the particles move farther apart. In this model, the particles themselves don't change size.
I don't think that the continuous model can help us very much with gases. It is unnecessarily complicated and doesn't hold up well to experiment. Usually when we are developing models in science, if two explanations are both supported by the evidence, the simpler model is the one that is adopted. This is known as Occam's razor and is the principle proposed by William of Ockham.
Okay, but if the particle model can explain the behavior of gases, if it's a good model, it must also be able to explain the properties of matter in other states, liquids and solids.
Right. Let's look first at liquids.
In our last session, David demonstrated how hard it is to compress a liquid. Applying the particle model, what explanation do you think might account for this property of liquids?
Look at what happens there. Now, can you draw a picture to describe the other thing that you did here, which is that if you have water, what happens? Can you push it? Can this guy get cramped together? Can I push this?
Yeah. It's the
I
same
can?
thing, kind of like air.
Okay. Draw the air. Okay.
Like right there.
Okay. All right. And what does the water look like? Can I push it further here? Like
No.
this? No? Why not?
Because the water
Mm-hmm.
is stopping you from moving it.
Oh, the water's stopping me from moving it. Was the air stopping me from moving before?
Not really.
Not really. Okay.
Air can be pressed. Water cannot be pressed.
David is absolutely right. Under everyday conditions, air can be compressed, but water cannot be compressed very much. However, David offers no explanation for why they behave differently, and his drawings give no indication that he's thinking in terms of particles. Rather, they look like a continuous model. How can we explain the non-compressibility of liquids?
Imagine a gas, perhaps the air inside this balloon. Imagine that at the microscopic scale, the gas consists of tiny individual particles with relatively large distances between them. The particles are constantly moving, colliding with each other and with the walls of the balloon. Now imagine a drop of liquid. Picture the same particles, this time packed very closely together. So closely together that in fact, they're touching. They slide and flow past each other. Any possible gap is quickly filled by particles that slide in from any direction. When we push from the outside, the particles resist the force, since they are already tightly packed. This explains how water can flow, but why, when it's tightly enclosed, it can't change its volume. If the particle model is going to fit observations, it has to explain how matter can change from one form to another.
It's something we observe all the time. Beads of water collecting on the mirror in the bathroom. Candle wax melting and flowing, and then solidifying in the candle holder. Water boiling on a stove. Any model that we put forward has to be able to account for all of these changes.
Let's observe what happens when a beaker of water is placed on a hot plate. While you watch Ariel, compare her model of matter with ideas you might have heard from your students.
Now, do you notice anything going on in there?
It's bubbling, and I know why it's bubbling.
Okay, why do you think it's bubbling?
Hot air is the way that thing's cooking, and hot air always goes up, and as it's going through the water is surrounding in these little enclosures, which we would call bubbles. Bubbles go to the top, exposed to a more regular air.
Okay.
They go pop, pop.
Okay, you're telling me those bubbles are full of
Air.
hot air?
Yeah.
Okay, and where does the air come from?
From
Oh,
this
careful
thing.
there. There's no air that can go through that glass. That glass is like incapable of letting air through it. Just like when you blow up a basketball, the air doesn't come out of the basketball sideways. So there's no air that's coming in. So where do those bubbles, do you think, come from?
I think when that thing was filled, it already had air in it, and when you put the water in on top of it, it got buried in there, and then you put it on something hot, and the heat can still get through, and it heats up the air, which then rises in bubbles.
Some people I've interviewed say that in those bubbles that you see,
Yeah?
that's not air. It's never air.
I don't know what they're talking about.
So what would you say to that person who says those bubbles are full of water vapor?
I'd say that at inside the water there is air and it rises to the top. The water then evaporates and changes into a gas called water vapor.
Ariel is convinced that somehow air was trapped in the water and is released when the water is heated. This isn't too far-fetched. A lot of children think anytime there are bubbles in a liquid, they have to be made of air.
That beaker was boiling for a long time, and a lot of bubbles came out of it. If I boiled away a liter of water, I'd get about 1,700 liters of bubbles. Is it possible for so much air to be hidden in that beaker of water? I think we could agree that those bubbles are not air. Let's see if our model of particles can be extended to provide a better explanation.
Have you ever noticed how droplets of rain tend to bead up and roll down a window? If so, you've probably noticed how water has a little natural stickiness. In other words, when one droplet of water comes in contact with another, the droplets tend to merge, as if they attract each other. The particle model also proposes that the particles in many liquids, like water, have attractive forces that tend to hold the particles together.
This would have to be the case. If there were no forces holding the particles together, everything that is solid would just fall apart and crumble. When water as a liquid is heated enough, many molecules together form a gas bubble. So the bubbles are not air, but water vapor, in which the molecules are pushed further apart than when they are in the liquid state. In a gas bubble, the average distance between water particles is much greater than in liquid. Let's review some of the characteristics of the particle model of matter that we've proposed so far. Matter consists of tiny particles. These particles are surrounded by empty space. There are attractive forces between these particles.
The process of a liquid changing to a gas and back again is key in lots of topics in the elementary curriculum, including the water cycle. We'll visit Lindsay Newton, who teaches 3rd grade in Hudson, Massachusetts, to see how this idea is tackled in her classroom.
Okay, so let's think about the other day when it rained. Do you remember when it was raining out? And then the next 5 minutes later, we were able to go outside for recess. Well, you guys were all confused. The ground was dry, and about 5 minutes earlier, the ground was wet. Well, what happened? Why is the ground dry now? Alex.
Because the dirt and the grass absorb the water.
Okay, so you think there's something happening with absorbing. All right, anyone else have a thought? Lindsay, what do you think?
After it rains or something, it goes back up into the cloud and wait until it fills up and then it do that again, so it probably got dry from that.
Oh, so how do you think that happened?
I don't know.
Okay. What we're going to do today is we're going to talk in small groups. Okay, you're with your group, and you're going to talk with your group about what you think happens to water after it rains. Okay, we talked a little bit about this. You're going to come up with 3 or 4 good ideas with your group. You're going to write it down on the paper that I'm going to pass out to you. And then we're going to check back in and share those things to see if they're different than what you just said.
And I think that the clouds get very low to try to pull the water up. It's easier. And then they become medium and then high.
Okay. What other ideas did you guys write down in your group?
After it rains, some of the rain would go into the lake and then the sun would absorb some of the water.
I think the clouds bring it up because, like you said, if it's cloudy and it rains and the sun doesn't come out, I think the clouds would suck it up too, would bring it up to the...
Okay, so that's another thought you guys could write down.
First it rains and gets the grass wet, all wet. Then the sun absorbs the water into the clouds, and when the clouds are full, it rains again.
Okay, so is that different than what you said in the first thing? What's the difference?
One absorbs when it's in the grass, and one absorbs into the cloud. I think it, like, somehow it turns invisible and then goes up, but you can't feel it when it goes up.
It's like the clouds drinking it. It's like taking up the moisture. Like one of us drinking water. But she said you can't see it. When I drink something, I can see what I'm drinking. But moisture is like, it's air that's wet, steam. It's like steam, sort of. Okay. Damp. You're saying mist, you're saying steam. Yeah. I think I can see those things.
It's mist, actually, yeah. Mist and like moisture water.
If it goes in the soil, it like makes the roots grow, like makes grass grow.
But doesn't
it goes in the dirt.
Okay,
Yeah.
so that's probably part of where some of the water goes. So what if it's a rainy day, and then it stops to rain, but the clouds are still out, and the ground dries, and there's not really a lot of sun out? What's happening then? How does it dry if the sun's not really out that strong?
Probably if the sun isn't out, then the rain would go into the soil before the sun could get it back into the clouds.
So you think you need the sun for things for the rain to disappear or leave?
Yeah.
Students feel that the heat from the sun is necessary to make the water evaporate. Is this true?
As we saw in the example of steam on the bathroom mirror, water can become a gas, then change back into a liquid. We'll return to Lindsay's classroom for a follow-up activity to the evaporation discussion. In this case, each group of students will look at 2 cups of water, one warm, one cold. Can we add the idea of heat to our model and apply it to changes of state?
Think about when you have a glass of lemonade on a hot, sunny day. Hot sunny day, you have a glass of lemonade, you go out to the pool, you sit down, you dive in the pool, you come out. What does your cup look like? What does your cup look like, Jocelyn?
It's all foggy around the edge, and I think I found out why. Because when there's coldness around hotness and they mix, it makes fog.
Okay,
Like
do
creates.
you mean fog or do you mean wet, watery type
Wet,
of thing?
watery, like thing.
Well, we're going to do a little experiment today. Each group is going to get 2 cups, and they're going to have 1 cup of room temperature water and 1 cup of ice water. You're going to observe what happens to the cups.
There's fog on it. You can draw on it.
I think it's gonna like ice up.
If you leave it in the freezer or something like that, it'll freeze up.
Yeah, cause like but on this one it doesn't have any fog or anything in it because it's room temperature water. And or maybe it's because that one has an ice cube and that one doesn't. That one keeps it cold, and the cold air makes it be foggy. And the hot air doesn't, like, a hot air can't get any fog. I kind of pictured this is winter, this is summer. When it's summer, I never see fog, so this doesn't have any fog. But in the winter, it has a lot of fog. That's why we can see through this one, because it has no fog in it. And we can't see through that one because it doesn't, because it does have fog in it.
These students don't seem to agree on an explanation for where the condensation came from. But they do notice that the cold glass collects water. How can we explain this with the particle model?
This explanation depends on one aspect of our model we haven't talked much about so far, whether the particles are stationary or moving. Let's do an experiment to try to answer this question.
What happens when I add food coloring to this still beaker of water? How can our model account for the fact that the dye spreads evenly throughout the water, even though we haven't stirred it or touched it? Could it be that the particles of water are moving and that this motion distributes the dye around the container?
Russell Springer, a 5th grade science teacher in Newton, Massachusetts, has prepared a classroom demonstration that will prompt some thinking about this question. He's mixed a small amount of machinist's oil into water and placed a drop under the microscope.
All right, so here's our liquid. And I'd like you guys to, if you would, take a minute, just look at what's going on there and decide what you think is going on there.
Well, it looks like they're trying to go to each other so they can make bigger molecules.
Okay, so they could squish together, yes?
They're all moving around the whole thing. Like, first it's moving that way, then it moves that way, and then...
Okay.
It kind of looks like living organisms, but droplets of water with holes in the middle of it.
Okay, so it kind of looks like some droplets of water with holes in the middle of it and some
Like a donut.
living creatures, like a donut, and some living creatures, yep.
To me, it kind of looks like a kind of a foggy night with little stars moving around.
Okay, you might want to think, what is making them move, first of all, and then what are those little Cheerios?
I might think that in some way they're magnetized because they're like kind of pushing off each other and not completely coming together. And I know that's kind of what it's like when you take two magnets and use the opposite poles to push them against each other.
I'm not sure, but my guess would probably be that the oil is going to one side and the water and other ingredients to another.
Okay, so that's because the oil and water don't mix there, maybe.
Or they're moving together.
Or they're moving together. What else?
It's like water, because water tries to connect, and it's trying to connect like water.
Okay, so water likes to stick to itself.
Yeah,
Okay,
so
that's
it's trying
interesting.
to group up.
Okay, yep.
Well, you said there was gas in there, and, well, doesn't that kind of make cars move?
Yeah.
So maybe somehow they're moving...
So maybe it's moving
By
like a
that?
car moves. That's interesting.
Well, oil, also, like when you feel it, it feels really slippery, so maybe it's like sliding around.
Okay, so maybe it's sliding around in there.
Some students believe that the little blobs of oil were moving on their own. Even though these students didn't look at any other kind of test object besides blobs of oil, scientists have found that the pattern of motion for any sort of very small object in water is the same. Russell uses machinist's oil, as it's easier to see this movement in water. The oil droplets are small enough so that this motion is a little uneven. Larger droplets have so many more particles hitting them that the collisions even out, and the larger particles don't appear to move. Let's return to Russell's classroom. His students are pretending to be water molecules. A larger object, a blob of oil in the shape of another teacher, is being introduced into the container of water.
So he's going to have to break through this water. Mr. O is going to be a droplet of oil. Can you guys please move around again like you were? No, you guys are, he's not holding hands. Yeah. But what's going to happen? Oh, you guys bump into him. You can bump into him. Yeah. Now, stop right there.
When we move, we break apart.
Well, you might break apart, but you come back together really quickly.
Yeah, it's still moving.
Yeah,
It's moving. No, that's right. That's right. Mr. O, you're my oil molecule. Can you please leave the water? But did you notice, did anyone do this to Mr. O while he was in there?
Yeah.
Does that remind you of anything we saw recently? What? What was bumping?
Well, the water and the oil. Yeah, and the oil.
Where did we see that?
On the microscope.
Okay, so yeah, actually, he would be moved around a little. And there might be someone on the other side bumping into him that would move him around a little more.
I think these two examples, the motion of the small droplets of oil and the dye in the water, are pretty well explained if we decide that the particles of matter are constantly moving. In fact, I think we should add this to our list of characteristics of matter. If we conduct a further experiment, we can see that this motion is related to temperature. If we add dye to two identical beakers of water, one cold and one hot, the hot one will distribute the dye much faster than the cold one. I propose that we define temperature as a measurement of the average motion of the particles. The faster the particles move in random directions, the higher the temperature. We'll explore this idea further in a later session.
Some of the particles move faster than the others. When water evaporates, the particles moving the fastest, if fast enough, break away from the surface of the liquid and fly away to form a gas. What about solids? What could explain the property that liquids can change into solids that hold their shape? Well, let's imagine a liquid with all the particles moving about in close contact. Let's then imagine slowing them down. We find that something binds one particle to another to form a fixed structure. No longer do the particles flow past each other.
In today's session, we've just begun to scratch the surface of the ingenious idea of particles. In fact, the physicist Richard Feynman said, "If in some cataclysm all scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures, it would be that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another." Please visit our website at www.learner.org to find out more and seek answers to questions that you might have about the particle model of matter.
In our next session, we'll look at the success of the particle model to explain condensation, evaporation, and changes of state. We call these physical changes. We'll also introduce another important concept to help answer the question, can matter simply disappear?
See you next time on Essential Science for Teachers.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.